Okay, welcome back everyone. In this series of videos, we're going to be taking a look at Newton's laws of motion. And so some of you might know this already, but I'll just leave this with you to start. May the mass times acceleration be with you. So for many of you, this is going to be a review or a reintroduction. And in this first part, we want to look at what's the concept of force and why are forces vectors? What is the significance of net force and what happens when the net force is zero? Can an object be moving and have zero net force? And what's the relationship between the mass of an object, its acceleration, and the net force acting on it? Finally, what does it mean for forces to be an interaction between two objects? So we'll start out with the question, what is a force? Well, it's just a push or a pull on an object. And unbalanced forces cause objects to accelerate. They can speed up, they can slow down, and they can change direction. And it's also important to note that force is a vector because it has a how much and it also has a which way. Force is also an interaction, meaning that it takes two objects to have a force between them. You can't pick yourself up. Someone else has to pick you up. So we'll talk briefly about the different types of forces. First, we have contact forces, which are direct contact between bodies. And so we're talking about things such as the normal force, friction, and tension. And we'll get into these details a bit later on. Then, the other major category are field forces. And these act without the necessity of contact. For example, the force of gravity, the electromagnetic force, and the strong and weak nuclear forces. And so really the question is there really any such thing as a contact force? Because when you break it down, things like the normal force or friction or tension are really just versions of the electromagnetic force. So we'll get into that in a little bit. Another major concept to review or introduce is the idea of equilibrium. So if the net force on a body is zero, it's in equilibrium. Now, one way to find the net force is to consider my picture right here. So we have a force and we have a net, so that's the net force. Get it? Haha. So if the net force on a body is zero, it's in equilibrium, and usually we'll write the net force in one of two ways. It'll be either written as the sum of the forces, or it'll just be written as F net. Now both of these are vectors. So if that net force is zero, we have equilibrium. However, an object in equilibrium could be moving relative to us, or it could be at rest. So even though the net force is zero, that doesn't tell us anything about the object's velocity. Okay? So we'll see in a moment that we could have constant velocity, which is either zero or non-zero. Okay, so we'll start talking about Newton's laws, and we're going to first look at Galileo's thought experiment. And so this is from the physics classroom. And Galileo said, well, if I roll a ball down a hill, if it's got a steep angle on one side and the other side, then if we could get rid of friction, then the height that you start at would be the same height that you end at. But what happens if you reduce the angle of the opposing incline? Well, the ball must roll further, but if there's no friction, it'll still keep going. But then what would happen if the other incline wasn't an incline at all? What if you had a straightaway? So if a ball stops when it attains its original height, then this ball would never stop and it would roll forever in the absence of friction. So this thought experiment by Galileo eventually led Newton to his first law of motion, which he stated as the law of inertia. And he said, a body in motion stays in motion in a straight line unless acted upon by an external force. Okay? And we often apply this, such as in our previous unit, to velocity, such as the velocity of a projectile in flight. So that's the first law. Sometimes we say objects in motion stay in motion and objects at rest stay at rest. And the important thing is that this won't change unless we have an external force. Okay, so Newton's second law. Now this was experimental in nature, and Newton determined that a body accelerates when acted upon by a net external force, and that this acceleration is proportional to the net force and is in the direction in which the force acts. So we could say that A is proportional to F as vectors. And this is often applied to the vertical component of velocity for projectiles. And commonly put, we write this as the sum of the forces is equal to mass times acceleration. So these are vectors. Okay? So the sum of all of the forces acting on an object is equal to ma. And these are vectors, so we have to use all the tricks that we learned about for combining vectors. Finally, we come to Newton's third law. Newton's third law states that for every action there exists an equal and opposite reaction. If A exerts a force F on B, then B exerts a force of minus F on A. In other words, if we have two objects A and B, then the force of A on B is equal to the negative vector of the force of B on A. So if you push a wall, your hand would be A, the wall would be B, and the wall will push back with an equal and opposite force. So that's Newton's third law. And we're going to be using this a lot, especially when we do collisions, but especially in all interactions between two objects. So let's clear up a couple things, and then we'll look at some example problems. First of all, inertia itself is the resistance of an object to being accelerated, but we quantify that with mass. So mass is sort of the physical quantity to which we ascribe inertia. Mass is usually measured in kilograms. Okay, so weight is actually the force of gravity on mass. So that's the force of gravity on a mass. Now inertia we don't really use as a variable in linear motion, but you could think of inertia as kind of being equal to mass, which is proportional to weight. And so we'll talk about exactly what weight is in a little bit. Okay, so let's look at an example of using the first law. And we'll have to change your pen color here. So we have two forces, F1 and F2, given by those unit vectors measured in newtons, and they act upon a body of mass 3.0 kilogram as it is moving at constant speed. What do you know must be true? Well, the fact that we have constant speed leads us to know that the acceleration must be zero. And this leads us to know that the net force, or the sum of the forces, must also be equal to zero. Okay? And this is sort of a combination of Newton's first and second laws. Okay? And so what we can do is we can take a look at this and add up F1 plus F2 and see if the sum of those forces is going to come out to zero. So that's going to be actually 5i hat minus 8j hat minus 7k hat newtons. Therefore, there must be a third force. And we know that this F3 has to cancel out the sum of F1 plus F2, so it has to be negative 5i hat plus 8j hat plus 7k hat newtons. So that's the conclusion that we have to come to because the net force must be 0. So if we take our F1 plus F2 and then add to that F3, we should result in 0. Okay. So let's do an example problem for Newton's second law. Okay? So now we only have two forces, F1 and F2. No other forces act on the body, and so what do we know is true? Well, we saw earlier that the net force, namely F1 plus F2, is not 0, but as a matter of fact, the net force was equal to 5I hat minus 8J hat minus 7K hat. So what this tells us is that there must be an acceleration. Let's see if I can spell today. And this acceleration, A, is going to be equal to the sum of the forces over the mass, because F net equals ma. Okay, so this acceleration will basically be, if we have a mass of 3 kilograms, it'll be 5/3 I hat minus 8/3 J hat minus 7/3 K hat, and that's going to be measured in units of meters per second squared, because the force will be newtons and the mass will be kilograms. Okay, so something to point out here is that this is the exact same direction as the force, because mass is a scalar. It doesn't change the direction, and it's always positive. It's a scalar, therefore acceleration and the net force are in the same direction. And this is very important to remember. Okay, so we'll do one more example problem. And this is the third law. So a tug-of-war team ties a rope to a tree and pulls hard horizontally. We'll represent the team with just one big person to create a tension of 30,000 newtons in the rope. Suppose the team pulls equally hard when, instead of a tree, the other end of the rope is being pulled by another tug-of-war team, such that no movement occurs. What is the tension in the rope in the second case? Well, it's just still going to be 30,000 newtons. Because if you think about it, in the first case, we had the tree and the rope and the person, and the tree would be basically pulling the rope with the force of 30,000 newtons in order to have 0 net force, because the rope would be pulling this way with 30,000. And the same would be true if we replace the tree with the person. Okay, so we're going to take a pause here, and then in the next set of videos, we're going to start breaking down how to use Newton's second law, and then looking at different types of forces in various situations.